Next, for those who have sent their project choices to our TMs, and we're gonna, if you choose to do the Kaggle competition, we plan to release the link, invitation link to you by early next week, so that you can start to play around it. But if you choose to do other project, exploratory project, you still have time to think. Again, if you feel unsure about the choice of project, I want to listen to my suggestion, or listen to our TM's suggestion. They all have taken this class before. They all got very good grade. So do not hesitate and come to the office hour to have a discussion. Okay. Let us continue with the ensemble learning, right? So in the last lecture, we gave a start for this topic. So the takeaway message we start with the boosting, right? So the takeaway message of boosting is two heads are better than one. That's it. So, but from computational learning theory, people are very beginning. They are curious to know like whether I only have a collection of weak classifiers. By weak classifiers, we mean that its performance is just slightly better than random classifiers. Right? If through a coin, just say positive, negative according to heads up or tails up, right? So this is a random classifiers. If we're doing binary classification, you know it's just 50% accuracy. So weak classifiers means that I only have like 40%, 45% accuracy, slightly better than the random classifiers. The interesting computational learning theory question would be like, can we derive a much stronger learning algorithm with all of those set of weak classifiers? And the answer is yes. The answer is yes. And then there's a line of research on that, and spend like about 10 years efforts. It comes our very widely used, very successful boosting algorithm called AdaBoost, which is the focus of our class today. So from this brief history of the development for AdaBoost, we can also see how theory takes a role in boosting the advancement of some discipline, right? So from our side, okay, we might be more interested in how the algorithm procedure is doing, right? And how do we implement it? How do we debug them on data and say, wow, our performance is really good. I feel I'm the god, right? But actually, you need to also appreciate those theoretical people who give this original contribution. Otherwise, they won't. Otherwise, we cannot arrive at this, right? Okay, that's why we have to learn a few seemingly more abstractive concepts. So we're not theoretical class for machine learning, but at least we need to know a few key concepts on that, so that you are ready to go deeper into that further if it's necessary for you. Okay, so now let us talk about the AdaBoost algorithm. Right? So we're going to use a very simple but concrete example to show the intuition of AdaBoost. Then we'll jump into the algorithm detail. And we'll briefly discuss why it works. And interestingly, you'll see the behaviors of AdaBoost is a bit different from what we have learned about the overfitting behavior. So you see that although AdaBoost can overfit the training data very well, it seems that doesn't hurt its generalization performance. As to why, there's still no answer right now. So this is still an open research question. But this is what we have observed from AdaBoost. Okay. And then we're going to talk about another type of ensemble learning. It's called bagging methods. Okay. So this is our top example to showcase how AdaBoost works. Right? So suppose this is our training set. So our training set is just those points, right, in the XY plane. So positive labels, negative labels. So we have 2, 4, 6, 8, 10. Okay, we have 10 training points and scattered in this XY plane. So our weak learner is simply a line parallel to x-axis or y-axis. So you can imagine how weak it is, right? Even it cannot be an inclined line. It must be parallel to axis or x-axis or y-axis. So that's our weak learner. Okay. So we're gonna learn, iteratively learn a set of such axis parallel lines to perfectly fit this training data. We'll see how we do this, right? So initially, we're gonna set all the examples to be equally important. Right? How can we the importance of a training example? We just use a weight, right? So we have like 10 examples. So initially, we set the weight for each training example to be 1 over 10. So 1/10. Just sample weight, right? So you can imagine I can tune the weights across those examples, right? And different set of weighted examples will end up with different weight classifiers. That's how we continuously to produce different weak learners. Okay. So initially, we'll set all the examples to have the equal weight, which is 1 over the size of trained data. Here is 10, so it's 1 over 10. Okay. So then I train a weak learner axis parallel line and find the best weak learner which can fit this training data. Okay. So it turns out to be a vertical line and stay here. So we denote this line to be H1. So this is our first weak hypothesis, right? So obviously H1 is not that perfect because it cannot perfectly fit the training data. If you use training data to do the prediction, you'll find, okay, I made 3 mistakes here, right? These 3 positive examples are misclassified by H1. So then we can compute these mistakes, and this is an empirical error, right? From what you have discussed, the basic definition in computational learning theory is empirical error is 0.3. We denote it by epsilon 1. Right? So now we proceed to the next round. Right? So for the next round, we're going to adjust the weights for those examples. How can we adjust it? So now that those 3 examples are misclassified by the first weak learner, right? So in the next round of learning procedure, I'm going to try my best to avoid making the same mistake. Right? That means I want to increase the importance of those misclassified examples. But meanwhile, because all the remaining examples are correctly classified by H1, right? To me, it's not that important. As important as those misclassified examples. So I'm going to downweight the remaining examples which are correctly classified by H1. So this is the first step in our second round. So for the next round, we're going to increase the importance of the examples with mistakes. Meanwhile, we downweight the examples that our H1 got correctly. So this is the idea. Okay. So now, given those set of reweighted examples, I'm going to train another weight classifier, another axis parallel lines, right? I'm trying my best to find out the best weight classifier which can fit this set of weighted training examples, right? So it turns out that I find another horizontal line but at a different location. Right? So how many? So right now, first question: do we correctly predict all the training examples? No, right? So how many mistakes our second classifier has made? 3. 3, right? Then what is the empirical error?
less than 3.3. Less than 0.3.
Why is less than 0.3?
Because the weight of those positive are increased.
Yes. Yeah. That's something we need to take into account. So don't compute the empirical error as like normally defined empirical error. Here we need to compute weighted empirical error. So our second weak learner, H2, has misclassified 3 negative examples here, right? But we're gonna take into account their weights into the computation of the training error because those 3 negative examples are downweighted at the beginning. Why? Because they are correctly classified by H1, right? So we downweight them. We only upweight those misclassified examples by H1, but those positive examples has already been correctly classified by H2, right? So that means, okay, all these 3 examples, their weights are downweighted. So it must be less than 0.3, right? If they are equally weighted, okay, 3 out of 10, okay, 0.3. But now they're downweighted. So their total weights will be less than 3. So here the error is 0.21. So I'll talk about how to compute it immediately. So don't get urgent. Okay. So here we use dt. We use dt to denote the set of weights at round t. So remember, because we'll just weights in each iteration, right? So each iteration we're gonna have a different sample weights set, right? So we use dt to represent the set of weights and 1 for each example. Right? And now I give you how to compute the weighted error. So it is 1/2 subtracted by 1/2, and then you compute over all the training examples, and each summation over all the training examples, and each summon is the weight of the sample, multiplying with the true label y with the prediction of your weight classifier h on the x-side. So why this is reasonable? This is something we need to address right now. Right? So why is this reasonable? So first, we need to consider 2 cases, right? So what's the value of this product? I mean, the blue terms. When we make correct prediction and when we make wrong prediction. Right? So remember, we're assuming we're doing like binary classification, and the yi is either positive 1 or negative 1, right? And also our weight classifier is a binary classifier as well, so its output label is either positive 1 or negative 1, right? So when we make a wrong prediction, what does it mean?
The product will be negative.
Yes, right? The product will be negative because y is not equal to h of x, right? So if y is positive, then h of x must be negative, right? If y is negative, h of x must be positive, right? So their product must be negative, right? And because their absolute value is simply 1, because it's labeled. Right? So in that case, we have this product to be simply negative 1. If we make a correct prediction, no matter the true label is positive or negative, this product will always be positive. Why? Yes. Both are positive 1, y h of xi are 1, or both are negative, right? Negative, and that was positive. So, so I have 2 cases, right? First, when our classifier makes a wrong prediction, then this true label multiplying with our prediction is going to be -1. Otherwise, it's positive 1. Right? So now, taking this effect into our account, now can we justify why epsilon t should be defined in this way. So I will give you the answer directly and give you a hint how to derive a link to this. But after the class, I strongly recommend you to show this. It's not very hard. It's actually you need to just sit down, calm down, and think of it for 2 minutes. Okay, so we can show that the weighted error is equal to the weights for all the incorrectly classified examples. That's it. So does it make sense? Is it reasonable if I define a weighted error like this? It's very reasonable, right? Oh, one thing I should emphasize again. Okay, those weights are normalized, meaning that the summation of the weights over the entire data set is always 1. Be aware of this, right? It's not some arbitrary value. You must ensure that the weights across the entire training set, their summation must be 1, so they're normalized. So now you can say, okay, this weighted error is still between 0 and 1, right? And it's just the weights of all the wrongly corrected samples. But how can we derive from this definition to this definition?
Well, so if they're the same, like the product of them is going to be positive. So you can think of like, let's assume like a case where they're all, where like everything is classified correctly. Then like the summation of that is going to be equal to 1.
Yes.
And so the error is 0. Yeah. And then if we think of the other case where everything is misclassified, the sum over like the distribution is equal to -1. So the error will be 1, and they can think of like, if it's like mix and match, it's like proportional to like.
Yes. Very good thought. Yeah, you're right. Yeah, it's a good way to think of that. Right? It actually correctly reflects what we sense about error, right? Yeah. And next step, you can continue to think of how to formally prove this. So I just gave you an idea, and then you can, after class, you can spend 2 minutes, use your pencil on paper to derive it. It's really not tricky, right? So basically, you can separate this summation into 2 parts, right? The first part is the summation over the correctly classified examples, right? A second summation is over the incorrectly classified examples. Both has the same form, but the range of the samples it sums over are different. So you can imagine that the first part, the summation over the correctly classified examples, can be rewritten as 1 minus the summation over incorrectly classified examples, right? And now you have a 1 minus 2 summation of incorrectly classified examples. And then you have 2 minus 2 summation over incorrectly classified, so that's why you have to have a factor 1 over 2 outside and cancel everything. You end up with this. So that's the idea. So yeah, to please try to derive it after class, and it will deepen your understanding of this definition. So why people give this definition? Because doing this is simpler to implement in your implementation. Our next homework 2, you're gonna implement your AdaBoost. So at that time, you will feel, okay, maybe using this formula is better.
This formula is just for binary classification.
Binary classification. Yeah. For multi-class, you have to adjust this formula. Okay, any other question regarding the definition? Okay. So now, we know this weighted error epsilon t represents how your weak learner in a run t or iteration t performs in predicting the training examples, right? And each error contributes to the extent how it's important, right? So because each error is related to each sample is the error is computed based on the weight of each example, right? The larger the weight, the more important the sample. So the larger the weight, if you misclassify an example and the example has a larger weight, that means okay, you made more mistakes on that. Right? So our next step will be further upweight the incorrectly classifiers by the second round, and then downweight all the remaining examples that are correctly classified by H2. A same procedure. But right now, our reweighting procedure is based on the classification results of H2. Right? So we increase the importance of mistakes and downweight the examples that H2 got correct. Right? So now we have the third weighted training set. Right? Although all the examples are the same, but their weights vary again. Right? Now I train a third weight learner, H3. Right? Oh, I got third weight classifiers, which best classify the whole training data. Now it turns out to be a horizontal line. Mm-hmm.
So why doesn't it get that case that's sort of like in like the leftmost plus sign? Because it looks like if you move the line, you could get that too.
This one?
Up and to the left.
This one?
Because like that's above all the other like negative examples.
Above, you mean here?
No, so
oh, here.
There's one that's like one positive example that's misclassified, but it seems like you could include it within like the set without adding any more errors.
You mean still using horizontal but different?
Yeah, like just move it down like to get the. So look at like the positive case that's like the leftmost one. If you move like the line down, you could capture that and then not include any more negative examples.
No, there are two positive signs. He said that if we move
If you move here, you have a.
Well, no, not through there. The left. So point your laser pointer at the leftmost one.
This one?
Yeah. Couldn't you include that one?
You move here?
Yeah.
Yeah.
You move here, so you have two negatively misclassified examples. What's your mean? Is what you mean?
Well, isn't that?
You have one negative here, one positive here, misclassified.
Yeah.
So right now we have 1, 2, 3. Oh yeah, we can do that. Yeah, definitely we can do that.
So why is it not done? Is it something with the weighting? Because isn't that strictly better than?
Yeah, you're right. But when we do the training, we have to consider the weights for those examples. Right. So if you move to here, move to here. Oh, I think so. You're right. Yeah, we can move here. We can move here to further increase performance of this, because we strictly reduce the one error, but we preserve the previously mistakenly classified examples. You're right. It's a very good point. So this is just this one showcase. We didn't consider very rigorously about which one is the best. But you're right. I can use my slides to move this a bit. But anyway, suppose we have found third hypothesis, which is now horizontal, and turns out to be this hypothesis is now the best one to classify the data, and obviously it's not perfectly classified. It does not perfectly classify the data. So we have we still have errors, and according to this definition to compute the weighted error, I got an error of epsilon 3 to be 0.14. Right? Again, why is for this specific classifier? Yeah, I misclassified 3 examples, but it's still not 0.3 because all the weights are repeated, all the examples are repeated, right? But from your suggestion, we actually can have even better classifiers. So it's even less than 0.2, like 0.2. So I guess the epsilon 3 could be even less than 0.14. Okay. So now suppose I just run 3 iterations. I stop. I have 3 weak learners, right? 1 weak learner, 2 vertical lines, and 1 horizontal lines. And then I will use these 3 weak learners to combine and get a stronger learner. So how can we combine them? We just do a linear combination. And for each weak learner, I'm going to assign a weight. Alpha 1, alpha 2, and alpha 3 for H1, H2, H3 respectively. So you can view like as prediction, right? You can view alpha 1, alpha 2, and alpha 3 are kind of weights for the prediction of each weak classifier. And then finally just count the majority vote. The label who has the majority vote. That's the whole framework. So think of the alpha values as a vote for each weak classifier, and the boosting algorithm has to somehow specify them. Okay. So here is the outline for boosting. Suppose we're doing like M training examples, M pairs of training examples, x1, y1 to xm, ym, and each instance is labeled a binary label, right? Either negative 1, positive 1. So suppose we run like big T iterations or big T runs, right? In each iteration, I'm going to construct a set of sample weights dt on all the M training examples. All those weights are normalized. Remember, this is very important. Otherwise, your implementation will yield very bizarre results. And then I find a hypothesis HT such that it has a small weighted error epsilon t. So by the way, I want to supplement what I have mentioned. So it's not required that to find the best weighted hypothesis for each iteration. So in many boosting algorithms, we say, okay, I'm just one somewhere. It's not required to be best. Okay. And then it has the weighted error epsilon t. But here we mentioned, okay, it has the smallest, it has a small weighted error, but it's not required to be smallest. Okay. And then after this big T rounds, we have collected the big T weak learners, right? And then I construct the final hypothesis by linearly combine this big T weak learners. That's the whole framework. Any question before we dive into the details?
How do you choose weights alpha 1, alpha 2, alpha 3?
That's the details we're going to discuss right now.
So before you said like based off of the votes that there's like majority rules kind of thing, is it really majority rules or is it just a combination of the
majority rules? Like if you're
one each, you pick one each at the end?
Oh no. No. So here we mentioned the final hypothesis is alpha 1 H1 plus alpha 2 H2 plus alpha 3 H3, right? So we actually combine all of them together. Okay. But we'll talk about like a detailed example. So another question regarding the general framework for this. I think it's pretty straightforward, right? So now let us look at the details, right? We need to know, okay, how do we determine the weight, the votes for each weight learner, right? And also how can we up the sample weights and down the sample weights, right? What kind of formula should we use, right? So let us first look at how can we assign the weights for the training examples in each iteration T. Right? So we have DT1, DT2 to DTM. So our principle is that at every round T, the weight learner looks for the hypothesis HT that emphasizes examples that have higher DT. That means I want to try my best to correctly classify those more important examples. And for those less important examples, meaning that they do not have bigger weights, I'm okay to misclassify them. So at the beginning, we mentioned that, okay, all the examples are equally important, right? So that means each training example will have the same weight, which is 1 over m. M is the size of training data. It's uniformly distributed. You can view it as distribution, right? It's uniformly distributed. And after T rounds, what we have in hand is that, okay, we have a DT, the sample, the weights of the samples in the round T, iteration T. And also we have the weight classifier, HT, that was just learned in this iteration, right? And also we have the error, epsilon T. The error, the weighted error of HT on this training set. So we're going to use these three variables to construct DT plus 1 for the next iteration. So we want from T plus 1 per round, we want to find out a hypothesis so that examples that were incorrect in iteration T are now correctly predicted by a new classifier, right? And also, that means we increase the importance of the misclassified examples by HT and decrease the importance of the correctly predicted ones by HT as well. So here's the formula. We construct DT plus 1 for each example I. By first, we reuse the weight from the previous round, the previous iteration. And ZT we can just put aside because this is just normalizer. We need to ensure, okay, all the weights across the training set, the summation must be 1, right? So we consider two cases. So first, if my prediction is correct, I mean by HT, then I'm going to downweight the current sample. So I'm going to downweight and multiply a coefficient which is exponential to the power of negative RT. So RT here is a positive value. So if you take it exponential to a negative value, it must be less than 1, right? So you multiply the previous weight by a coefficient less than 1, you are actually downweighting it. Does it make sense? If my prediction is wrong, right, for this particular example I, my learned hypothesis HT has made a wrong prediction. Then I'm going to upweight the example. And I multiply the previous weight by this exponential to the power of RT. So right now, because RT is bigger than 0, right? So actually multiply some constant bigger than 1, you will increase the weight of this misclassified example. So that's the schedule to adjust the weights. And the ZT here is just to normalize, to ensure that, okay, I can first compute all those reweighted samples and then do the normalization. So ZT is just normalizing. And then we can summarize these two cases into one formula by using the facts we have just discussed, right? We can just write it as I multiply the previous weight by this exponential term to the power of minus alpha t yi ht xi. Why? Why we can summarize in one form?
Because if it is correct, yt multiplied hft will be 1, and so the answer is the same as
Yeah, yeah. If you are doing correct prediction, this product, I mean the blue product, is simply 1, right? So it's downweighting. If it is incorrect, then this is -1, negative, positive, you're upweighting, right? Any question?
What is normalizing for ZT?
Okay, good question. So when you multiply each previous weight by some kind of coefficient, you are no longer guaranteed that the summation of those weighted weights still to be 1, right? But as I said before, right, we must ensure the reweighted samples, their weights summation to be 1. So you need to normalize them. How do you normalize them? You can compute, just cover this, right? You can compute for each sample I, this part, right? And just sum over all of those terms across the entire sample, right? Then this is ZT. Then divide it, then, you know, here they are normalized. Any other question? Okay. So, yeah. So our here must be 0, right? So ZT is normalization constant, ensures that the weights dt plus 1 adds up to 1, right? So then the remaining question is that how can we compute alpha t, right? So the alpha t is defined here. It's determined by the weighted training error, epsilon t. So it's half logarithm 1 minus epsilon t over epsilon t. So now I'll ask why alpha t is positive. In other words, what kind of assumptions guarantee that alpha t is positive?
Does epsilon t is less than or equal to 1 over 2?
Yes. Why?
Can you just calculate 1 minus epsilon t over epsilon t is at least 1 by multiplying?
Yes. From this definition, we can see that only when epsilon t is less than or equal to 1/2, you end up with positive alpha t, right? Positive or at least non-negative alpha t. Otherwise, alpha t will be negative. That's embarrassing. But why epsilon t must be less than or equal to 1/2?
Like the definition of epsilon t was 1 over 2 minus something.
That's not guaranteed for that. I can give you a very bad classifier to the epsilon t can be 0.8. It's possible.
If epsilon t is greater than half, then you're performing worse than like a coin flip. So I'm assuming that you can fit your data somehow it's better than just random.
Yes. Yes. So this relates to our key compute assumption. Actually, this is not some always truth. You should be careful to choose your base classifier. I mean, your base classifier can be weak, but cannot be arbitrarily weak. It should be at least better than a random classifier. If it is worse than random classifier, then your algorithm won't work. Okay. So because we assume like our weak learner always guarantees at least slightly better than the random classifiers, that means if epsilon t is always less than or equal to 1/2. If it is bigger than 1/2, that's the issue. Since epsilon t is less than 1/2 and value of alpha t is bigger than 0, this is the reason, right? So in your implementation, when you choose your weak classifiers, this is some kind of trade-off. You cannot choose very complicated models that won't make your Wishny algorithm work, but you cannot choose very, very weak classifiers. Even weaker than random throwing a coin, that's not a lot of swap. So eventually, this alpha t not only may serve the adjusting weights, but also serves as the final votes for each weak learner. So remember, for each particular iteration, we produce one weak learner, right? And finally, we're going to combine all those weak learners together. Each weak learner has its own weight. So alpha t is also its own weight. So see the two functions that alpha t take, right? First, it's used to produce the adjusted weights for the next iteration. And second, it's used to combine the current learner into the final hypothesis. So now we have known the details to construct a distribution dt on this M training examples, right? So in the last step, right? Suppose we have finished all the big T iterations, right? We're going to construct a final hypothesis by combining those big T weak learners, right? How can we combine them? Here's combination. So we have big T weak classifiers H1, H2 to H big T, and with big T values of alpha T. So how do we compute alpha T? As we just mentioned, right? We use this formula. So I say this value not only serves to downweight update the sample weights for the next iteration, it also used in the final combination of those weak classifiers. Right? And recall that each weak classifier takes an example X and produces either a positive one or negative one, right? So if you want to give the final prediction by combining them together, we just compute the weighted summation of their predictions. I mean, each weight or each vote will be the corresponding alpha values, right? Alpha 1, alpha 2, alpha t. And then we say the final value is positive or negative. If it is positive, I'm going to predict it to be positive. Otherwise, I'm going to predict it's negative.
Is like the horizontal and vertical line example, when you take the combination of all of them, is that like the equivalent of drawing like a diagonal line varying slope through the square?
I'm not sure for that.
Okay.
So I guess it's not. Why? Because later you will see when we do this combination, your training error will be 0. I mean, it draws a classification boundary which is quite complex. It will separate all the positive examples from negative examples. But from that, the original train said, I highly doubt that you can draw just a horizontal or diagonal line and well separate them. So we'll see the picture later. Okay. So is there any question regarding the definition?
How to make sure that summation is not 0?
0 here.
Yes.
Yeah, it's possible 0. When it's possible 0, you either can choose positive or negative. This is not. I mean, this is tie, right? This is tie, right? To tie both positive and negative values, and it's up to you to make a choice.
And for the definition of alpha t, why you use 1 by 2? What is for 1 by 2 partitions?
This part? Yeah, this is the constructed this part. Why we construct alpha t like this? We want to prove something. We want to prove that how the train error decreases along with the number of iterations. We'll see the result later. You'll see that okay, by constructing such kind of alpha t, your train error decreases exponentially with the number of the iterations. But someone asked, can I have other strategies to repeat and compute this alpha t? The answer is yes. But it's up to you. It's a novel idea. It's your research. Okay. Okay, now let us look at the full algorithm, like full detail of algorithm. Given that in your hand, you should be able to implement AdaBoost yourself, right? So we initialize in the first round, right? We initialize all the sample weight to be 1 over m. M is the set of training samples. That means all the samples are equally weighted, right? And then for the current iteration, right, we find a classifier, the weight classifier ht, whose weighted classification error is better than chance. It just requires that it's better than chance. It's not required that you must choose the best weight classifiers. Then I'm going to compute its vote for HT, right? Alpha T is defined here, right? And then we also use this volt to update the values of the weights for each training example, following this formula, following this unified formula. And then we finish the one iteration. We have obtained one specific weak learner and its volt. And then we go to the next iteration. We do the same thing again and again. After we finish all the big T iterations, we end up with big T weak learners, and we combine them together, where with each weak learner having its volt alpha T here. Okay, any question regarding the whole algorithm details?
How to make sure that HT is better than chance?
Actually, it's not like strictly guaranteed, but usually there are a set of choices, like decision stumps, like very shallow decision trees. As long as you have some like training procedure, you usually can make your classifiers to perform better than chunks. But it's not. I mean, again, this is not guaranteed. It is possible that you have very bad classifiers that gives you.
So what kind of algorithm do you use to find the pathfinder? Is it decision tree or
decision tree, decision stump? And the most commonly used weak classifiers are decision trees. They are most popular, but there could be any other choices. But here, a common practice will be that a reasonable classifier will always be better than a random chance classifier. If you choose a classifier such that end up with like prediction error is bigger than 0.5, then very probably you have some bad bump in your implementation, or you have a wrong processing criteria. Right? But still, like, do I have still a question like, do I have a decision tree or whatever other machine learning model? I guarantee that on any set of training data, I give you a prediction error is bigger than less than 0.5. It's not guaranteed. So that's why in a practical implementation, you should be careful. Say if I'm training a classifier, it turns out your alpha T is negative, then if I were you, I would just throw out this classifier. I won't incorporate it into my AdaBoost collection. Does it make sense? Any other question?
So we define the formula to calculate the error for binary classification problem, but what if there's like multi-classifier, maybe regressional problem? Does that calculation of the error still apply?
No, it does not apply. We have to adjust this algorithm a little bit.
Okay.
It's not covered in our class. So one possible, one straightforward extension I can share with you is that suppose I'm doing three class classification, right? So I'm gonna turn it into like 3 binary classification problem, and then I have 3 AdaBoost learner, right? And then I do 3 class classification. Then I use some decision procedure to choose the one I feel most confident. This is one choice. The other choice, I'm directly revising all those kind of steps, how we compute alpha T, how we compute the weights, those steps. Does it make sense? Any other question? So everyone is comfortable. Okay, so now back to your question, right? So suppose I have run 3 iterations of my AdaBoost. My weak learner is just those axis parallel lines, right? So if you combine them, right, by using the volts alpha 1, alpha 2, and 3, computed following the protocol just mentioned, right? This is your classification boundary. So you can say, although the boundary is kind of either horizontal or vertical, right? But in total, they give a very complex boundary. this nonlinear boundary. And it will separate all the positive examples and negative examples. So you can see the power of boosting, right? So even you have a bunch of very silly classifiers, if you can smartly combine them, they can still perform, behaves very complicated and very powerful.
So is it pretty safe to say that the more the like H1, H2 hypotheses you have, the more likely you are to overfit your data?
Yeah.
Or overfit the training?
Yeah, that's a behavior of the AdaBoost algorithm.
Mm-hmm.
And later we'll mention that although AdaBoost tends to overfit the data, but tends to perform well in training set as well. I mean, the generation performance still goes down, goes up, and won't be affected. That's something unusual from the observations over all the other classifiers. Yeah. So regarding the training error, right? Someone, not that you haven't asked, right? So the more weak classifiers we have in hand, the more likely your overfit the training data. The answer is yes, and actually we have like theoretical guarantee for this. So if you run AdaBoost for big T runs, I mean T iterations, big T iterations, and we denote epsilon T. I mean the empirical error, the weighted empirical error or training error by epsilon T, which is half minus gamma T, right? So as we mentioned, we require each weak learner is just slightly better than the random classifier, so we can define the weighted error as half minus gamma T. So then around all those gamma T's, if we pick up a lower bound of infinite amount of all the gamma T values, we take it to be gamma, right? And we can bound the training error of the final hypothesis, the one which combine all the T weight classifiers together, by exponential to the power of -2 gamma squared and T. So what does this bound reflect?
Gamma is not very important, but T should be large sum.
It actually verifies your intuition. Right? Someone asked, right? The more big learners I have, the more likely I overfit data. From this bound, it clearly shows, yes, that is. You can see, the more iterations I run, the smaller training error. And the decrease the training error has what kind of speed? It decreases exponentially to the number of iterations. Right? So you can imagine, like, when you run more and more iterations, you will produce more and more weak classifiers. Your training error of the final hypothesis can quickly decreases to 0. Right? So that's the behavior, typical behavior of the AdaBoost. Right? As T increases, the training error drops exponentially. The proof is not very difficult. It's just combine all kind of like inequalities we have known before. Right? So I won't introduce the details for this proof, but I uploaded the proof document in our course website. So if you're interested to investigate, you can just take a look. So from this bound, we can see that as long as we run enough number of iterations, we can perfectly fit the training data. You can imagine, like, we do not need large number of T. This kind of bound can go to be like very, very close to 0, right? This is the upper bound of the training error. So you can imagine the training error can be very easy to be 0. So this is a typical observation by running AdaBoost on practical data set. So x-axis represents the number of iterations, namely the big T, which is mentioned, right? And the y-axis represents the training error. So you can say, when more and more iterations are going, the training error drops very, very quickly, right? Very quickly. And also we can expect that, I mean, the final hypothesis is a combination of all those weak classifiers, weak learners in each iteration, right? For each individual classifier, with more and more number of iterations, the error actually tends to increase. So now problem comes, like concern naturally comes up, right? So now that our combination of those weak classifiers is so easy to overfit the trained data, it's likely to. You have a question?
Yeah. Is the increase in error, is that the weighted error that increases?
Yeah, the weighted error. I mean, the weighted error indicates that, okay, you can imagine that in the first classifier H1, right? It misclassified one example or two examples. So you have a weighted error, but in the next round, its weight is upweighted, right? It increases. That means your error. If you still use H1 to classify on the second set of weighted examples, your error increases, right?
Good not.
So this, you use the final weight to calculate all of these, or the weight at each?
The weight at each. So you say this is a number of iterations. So you can imagine, okay, at the beginning I have a classifier H1, right? So I will misclassify 3 examples, so my weighted error is 0.3 because every example is equally weighted. But next time, in the next set of iteration, the 3 incorrect classified examples, their weights are increased. And I use H1 to classify them again. What's the weighted error? It could be 0.4.
Yes.
So that's why the individual classifier errors tends to increase.
Okay.
Yeah. The individual, I mean, each weak learner in the final set. Yeah. This is just a typical behavior we can verify in practice. So now the question is that, as we have learned before, right? We know, okay, a classifier or a machine learner like tends to overfit the trained data. This is not big. This is not good sign. So typical learning curve is like this, right? So when you run more and more iterations for your learning algorithm, right? If your training error keeps going down until to be close to 0, your test error will at some point jumps up, right? It'll get increased. That means, okay, your generalization performance becomes worse and worse. Why? Because you overfit the training data. Those kind of noises in the training data kind of mislead your learning procedure. You end up with a hypothesis which does not perform well in predicting future unseen examples, right? So this is a typical behavior. This learning curve are observed in many classifiers, including artificial neural nets. Actually, artificial neural nets has very obvious behavior for this. And also, this can be well explained by our Occam's razor's principle and overfitting phenomenon. But for AdaBoost, this is kind of a unusual behavior. People have found that even when your test error decreases to exactly 0, your training error decreases to exactly 0, the test error won't increase. Sometimes even decrease, or sometimes it just keeps stable. This is an open question. So people have found in many practical data set this kind of behavior. Like even your training error goes down to 0, the test error can continue to decrease. That means you have even better and better generalization performance. So these range observations, are already from the AdaBoost, and people have come up a few explanations for this, but there's no, I should say, there's no ground truth right now. So if you're interested, you can take a look at Shapiro's paper in 1997. They provide one possible explanation on that. So any questions so far?
So like before you were saying your potential like H of T's could be different, like decision trees. They have to like decision trees features, or do you use the same features just in different orders and does it work? Or
The same set of features.
okay.
Yeah, the same set of features. The only difference is the weights of the samples. So remember, you guys have already started the homework 1, right? So you're asked to compute the weighted samples, like fraction counts, right? You know, you adjust the fraction counts. Actually, the weight is the information gain, no matter it's based on Gini index or whatever. It can change, right? That means that it can alter the structure of the trees. Okay, so I have a finished discussion of AdaBoost algorithm. Right? So to summarize, right? First, AdaBoost is simple, fast, and there's only one additional parameter to tune, just the number of the iterations. How many weight classifiers would you like to combine, right? And you can use it with any weak learning algorithm as long as they are slightly better than chances. But there are also some issues or potential problems when you use AdaBoost. First, the performance often depends on data set and the choice of weak learners. So this is important. If the weak learners are too complex, they may fail. If the weak learners are too weak, meaning that you might have problematic classifiers which give you, in many cases, just even worse than a random classifier, then it won't work. So, therefore, in practice, and from common practice, like people found that if you use the decision stumps as the weight classifier, in practice it works best. So what are decision stumps? Which we mentioned once, right? Decision stump just means one level decision tree. That means you only select one feature and split data once. That's it. The decision stumps. So if you just combine like a few hundreds or less than hundreds decision stumps to construct AdaBoost, it turns out the performance is really good and really robust. Right? But don't use too many decision stumps. Okay, so we have introduced the AdaBoost algorithm. Right? Hopefully, in the practical problems, in our next homework, you can implement by yourself and you can tune them on the real data to see how they behave in real data, okay, to give you a more sense on that. Right? So now we're going to introduce another type of ensemble learning approach. It's called bagging. And again, bagging methods are usually combined with decision trees as well. So what is bagging? So in generally speaking, bagging is kind of a meta algorithm that combines the output of multiple classifiers. So basically, I'm going to independently train a set of classifiers. And then I just combine their outputs. And there's no weights, different weights for different examples. There's no like iterative or sequential procedure. Like my sample weights in this iteration is determined by the results from the previous iteration. So that's boosting, right? But for bagging, the training are totally in parallel. You just pick up a random data set and train classifier. You got classifier 1, 2, 3, 4, 5. And when you do a prediction, you have 5 predictions, right? And then I'm just averaging them together. That's bagging, and even simpler than boosting. But it often tends to be empirically robust. And as to why it is robust, we'll explain later. Right? So, but here are many successful examples by applying ensemble. Right? For example, in 2009, the winner for this 1 million Netflix prize was a giant ensemble. So here's the general framework for bagging. So again, we assume like we have like m training examples, right? And we assume we run our algorithm backgrounds for t iterations. For each iteration, I'm gonna draw n prime examples from the original training set. training set. But how do we join these M prime examples? We draw them uniformly with replacement. And then when we have this set of random training examples, I train a classifier. I can use any classifier. We denote by CT, right? And finally, after these big T iterations are finished, we have big T classifiers. And then just construct final classifier by taking both from each CT. So that's the idea. So 2 questions. Right? First, what does it mean for uniformly sampling with replacement? The second question, how do we take the votes, right? So can anybody tell me what is uniform sampling with replacement? It's a statistical concept.
It's taking from the set and then taking another sample, but keeping the original set. So if you take a subset from the original set, you bring back the original values.
Yes.
So basically, you can have duplicates across sets.
Yes, exactly.
That's what that's saying.
Yes. With replacement, just means that okay, if you sample it, right? If you sample a ball from a collection of balls, after sampling, you can put the ball back and sample again. I mean, if you sample one red ball and you do not take it off, when you sample it, you just put the red ball again in the original collection, sample again. So that means next time you can sample the red ball again. So your sample set contains many duplicated samples. That's called uniformly sampling with sample with replacement. Without replacement means that okay, when you sample red ball, just throw it out. You can never use it again. Okay. So that means there could be duplications, right? And in particular, if M prime equals to M, meaning that the size of the random selected samples is the same as the original set of samples. This set of M prime examples is called a bootstrap sample. If you have taken a statistical course before, the bootstrap jackknives all comes from this sample procedure. So to give you a concrete example, right? So suppose this is our original data set x1, x2 to x5, right? 5 distinct examples. Right? And I set M prime to be 5. That means I'm going to random sample another five examples out of this original data set. Right? So this is one bootstrap sample. So you can see, at first time I random join a sample which is x1, right? And then I throw x1 back. That means x1 still has equal chance to be selected again. So next time I also happen to select x1. And the third time I select x2, and fourth time I select x4 because x2 is put back. So fifth time x2 has the same chance to be selected. So this is my bootstrap sample 1. Right? So we can say we have 2 duplicated examples x1 and 2 duplicated examples x2, right? And similarly, this is another example of bootstrap sample. I have 2 duplicated example x2, right? x3, x4, x5, and a bootstrap example sample set x3. So bootstrap sample means that okay, there could be duplications. They are not necessary. I mean, even I set M prime equals to M, they are not necessary to be identical to the original data set. So be careful. And then we construct a final classifier by taking the votes from each CI, right? How can we take the votes, right? So if you are doing classification, so you're doing binary classification, you have like 10 classifiers. 6 out of the 10 classifiers predict a positive label, and the remaining predict negative. So the votes for the positive and negative labels are 6 and 4, right? And then I use a positive example as my prediction because it has the majority vote, right? So remember here, there is no like weights for the outcome of each classifier. All the classifiers are considered equally important, equally competitive. And if you are doing regression, how can I do that? How can we combine them? Yes, average. Yeah, you can use actual median value is a very nice idea. But average is kind of like first choice, the straightforward choice. Right? So we just pick the average. That's it. So to summarize, bagging is a method for generating multiple versions of a predictor and using those predictors to get an aggregated predictor. So when you are doing regression, we just average over the versions for predicting numerical output. But as you just mentioned, we can do the median as well. Probably median is even robust, even more robust. Right? So if you're doing a classification, you just count how many classifiers, how many predictors give class 1, how many predictors give class 2, and how many class 3, blah, 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 and then choose the label who has the majority vote.
So if there's a tie vote between the classification, do you just choose an arbitrary?
You choose arbitrary, unless you have like a particular rule to do that. But if it's just like you have five positive and 5 negative, well, if you don't have any prior knowledge, you can randomly choose one. So each of those multiple versions is constructed by making bootstrap replicates of the learning set, and it uses this as training set. So as we just mentioned, it means we draw samples uniformly with replacement. So there could be duplicated examples in your each of the sample training set. And in practice, people have found that on both real and simulated data sets, on both classification and regression problems, bagging can give substantial gains in errors. That's why, as we just mentioned, in Netflix prize, right? The winner uses the giant ensemble. They might fine-tune a lot of several like highly predictive models, and they want to further improve performance and do the bagging. And when the bagging method is particularly useful, right? If your classifier is kind of complicated in that if you slightly perturbate your training set, the classifier can be changed significantly. Then to improve the robustness of your learning algorithm, it's better to use bagging. In other words, bagging mainly improves upon your algorithms in terms of robustness or reliableness. So the most commonly used bagging methods are mainly based on decision trees. So obviously we can construct a bagged decision trees, right? So how can we do that? We draw a T bootstrap sample set of the data, right? Each time I just draw randomly sample a data set from the original data set and train a decision tree. And then I got big T trees, right? Then we average the prediction of the trees on those samples. So you have 1, 2, 3, 4, 5, 6, 10 or 20 trees, right? So each tree has some predictions. But here we're using regression trees or binary trees who has the probability values, right? And then when we do the prediction, just average all the predictions. So here's the pseudocode to give you a reference to implement your bagged decision trees. So again, suppose we're giving a training set with m examples, and we designate the number of iterations. So for each iteration, I will draw m examples uniformly with replacements from the training set. So here we choose the m. We choose the number of the random generated samples to be the same as the training set size. So this is called bootstrap sample. We just mentioned. We denoted it by xt and yt. Then we learn a decision tree ct from xt and yt. You can use ID3, using card, or using others. But here, there's no need for you to prune or control the size of tree. So you can let your tree to grow arbitrarily large until it overfits the training data. It's totally fine. And after you have finished those big T iterations, you end up with big T trees, right? And then when doing the prediction, you either vote or you average predictions for regression. Any questions so far?
So I'm curious, is there any change in accuracy if the bootstrap sample is done without replacement?
Without replacement.
Yes. So you just simply take a subset that is.
It depends.
Yeah, I'm just wondering if there's been any examples of where doing without replacement makes a difference.
If you do it without replacement, there's an issue. I mean, it's like you don't have enough variability in the sample set because like you're likely to split data set, right? Split data set into several parts, and if for each subset of parts you train a regression tree or classification tree, whatever, right? So that means okay, this tree only captures partial information for that. As we will explain in the next class, right? Why it works, right? Why bagging works. So assume like each tree can utilize all the information data, and each tree try to overfit to the whole data set. But because the randomness in duplicated samples, each tree overfits in different aspects. But on average, their bias is still small. At the same time, the key argument is here. Because you do the average, your variance is dropped. So in total, you will see that our generalization performance is determined by two factors. One is bias, one is variance. The bias won't change, but the variance is decreased significantly when we take the average. Then in total, it will decreases. I mean the generalization error.
So it's almost expecting
Yeah, expecting.
an overfit on each of the trees, but it will balance it out whenever you get to the average voting.
Yes, I expect it. Because we will talk about like generation performance, we can only talk about on expectation, how it behaves. We cannot like take a special case as an example. Okay, so I believe that everybody is comfortable with this algorithm procedure, right? So we're gonna discuss why this simple strategy, seemingly silly strategy, works so well. Okay, see you on next tutorial.